If people are coming late, then they will miss a little bit of the introduction, but that's too bad. So this is our pleasure to have Patrick Pun from Singapore. So Patrick did his PhD in Hong Kong with Ouying Wong at the Chinese University of Hong Kong, and that was 6 years ago. To tell you everything, I tried to recruit Patrick when he finished his PhD for being a VAP, visiting assistant prof at UCSB. And he got a nice tenure track offer from NTU, and he chose to go to Singapore, which I understand. And now he's almost up for tenure, so time is passing, flying. And we're happy to having you, and you will tell us about non-local, fully nonlinear parabolic partial differential equation. And the screen is yours, Patrick.
Thank you, Professor Foucault, for the very nice introduction. And I would like to first thank Professors Ishiba and Foucault for inviting me to this virtual seminar. So I think it's a very good afternoon to all of you. So so it's my great pleasure to share with all of you about my latest research about non-local fully-nonlinear parabolic PDE. So it's kind of a special class of PDE, and it is basically inspired by a broadcast of economic and financial problems. So it's a joint work with my PhD student Nate Chen. So I would like to first have a very quick look at what is the PDE that we are interested in, and I will give you the motivation later on. So the PDE looks like this one, the equation one, and we know that PDE can be used to formulate a lot of problems. So I would like to really give you the general framework of this kind of PDE instead of a specific problem. So this talk will be focusing on this type of PDE. So what is the special features of this PDE? So when you look at the PDE here, so first of all, S and Y are the dynamical variables. So S is the time variable and the Y is the spatial variable. And the special features of this PDE is that there will also be T and X. So T and X will have the similar role as the S and Y, and first particularly, so T and X are like external parameters. So if there are external parameters, so solving the PDE seems to be easy because we can just treat it as coefficients or parameters. But now we have these three terms. So these three terms is to somehow replace the T and X by S and Y. Okay, so these three terms will actually bring in some essential difficulties. So it becomes not a very classical PDE. And I will explain about why we will be interested in the involvement of these three terms. And it's a fully nonlinear PDE because the F could be quite general, and overall, this is the PDE we are interested in. So without the T and X and also the diagonal terms, the equation one PDE will be.
Can I ask a question?
Yeah, sure.
You see, you will spend more than a minute on that slide. There is a lot of information here. I'm a little bit confused about S and T. So in the you have a initial condition, right? And
correct.
S is a time variable. You take derivative with respect to S.
Correct.
So S start at 0 because I see UT 0, but then at the same time you want S greater than T.
Oh, okay. I think there is a typo. This should be S and then less than or equals to T. But I think okay. The formulation here should be okay. I'm sorry. So here will be some typos, because let me share with you why I have this kind of typo, because the problem is usually formulated as backward. So this should be capital T, sorry. This shouldn't be 0. But sometimes if we consider from 0 to, if we consider initial value PDE problem, the later analysis is a bit easier. So that's why I revised a bit about the notation. But if we consider initial value problem, it should be S more than or equals to T.
It's a terminal value problem that you have in mind.
Yeah, correct. So I'm so sorry about the typos. Okay. So so this is the PD we are interested in, and if there are no TX and the diagonal terms, it will be reduced to a classical fully nonlinear parabolic PDE. And this is not the brand new PDE that we first investigate. Without the X dependence and the term, this one, the UYY term, the well-postedness of the PDE is established in this paper. So the motivation of this work is about the time inconsistent stochastic control problems. So here we are interested in maximizing the J cost functional with the SDE of the state process X. And the setting here could be quite general. And the J will take this form. And you will see that this is the J cost functional at time T and X. And the cost functionals, including the one-link cost functional and the terminal of cost functional, will depend on T and X. So that would mean that for when time involved, the preference of the agent will also involve. So that will cause the time inconsistency. And another time inconsistency is caused by this term, the G term. So if the G is nonlinear in the expectation term, it will also cause time inconsistency. So here I list the sources of the time inconsistency here. So if we have TX dependency in HG and capital G, so we will have the time inconsistency, and another source is the nonlinearity of G. So here the time inconsistency means that when we try to tackle with this stochastic control problem, Bellman's principle of the optimality principle is violated. Or we can put it in this way, local optimum is no longer the global optimum. Or we can say that the optimal controls that we determine at later time will be maybe deviate from the optimal controls determined at earlier time. So that is what we define for the time inconsistency. And this is the problem that we are interested in. And there are some applications, some economic and the financial application. So for the very first application is the Pearson bias preference, also known as the hyperbolic discounting. So it is actually classic work of the behavioral economic. And here we assume the agent's preference value of random consumption stream is this one. So here is the utility of the consumption, but in front of it is a discounting factor, discounting function, which will depend on the Pearson time. So a very interesting illustrative example proposed by the foreigners is that, so if I give you two options, one is to, option A is to give you an apple in 1 day, and the option B is to give you 2 apples in 2 days, then most people may prefer the option A. But if I say, prefer the option A. And if I give you another 2 options, option C is to give you an apple 1 year, and option D is to give you 2 apples in 1 year plus 1 day, then most people may prefer the option D. So the difference between option A and B and the difference between C and D will also be the same day, 1 day. But given that we have been waiting for 1 year, then then the option D seems to be also worthy to wait for other one day. So I think that is to explain the time that so the preference will actually be involved in time. So that is to explain why the time inconsistency preference will be important in our problem formulation. And second application is the well-known mean variance portfolio selection. So the agent's objective is to minimize the mean of the terminal wealth minus the least average coefficients times the variance of the terminal wealth. So if we actually we write the variance into the formula of the variance, it can be re-expressed as this form that will be fall into the general framework here. And here you can see the nonlinear term of this expectation term. So so this is a very classical time inconsistent preference, and we can even consider the state-dependent risk aversion. State-dependent risk aversion. So actually, there are a lot of people, researchers working on these two problems, and I would suggest the audience to check out this very recent survey articles. I think it has been just published a week ago, and the reference there. So when we are facing, when the agents are facing the time inconsistency, what can we do? So here the very seminal paper describes three types of agents. The first one is pre-committer. The second one is the myopic agent, and the third one is also our interest, is the sophisticated agent. So pre-committer is to solve the optimization problem only once at the beginning time, and then commits to the resulting strategy throughout the whole horizon. So in this case, we are trying to solve the problem, but of course we are aware of the dynamic setting, and we are trying to determine the optimal controls at the beginning time. So it will be optimal if we view the problem at the beginning time. So this is the pre-committer. Myopic agent is somehow disregard the dynamic optimality. So we are just treating the optimization problems in each period. So we somehow, for a long horizon, we discretize it into a number of small period, and then we optimize in each period. So we somehow disregard all the dynamic optimality. So it's myopic agent. And the first one will be somehow we cannot, we are unable to pre-commit, but we also realize that the dynamic optimality, realize that her future self may disobey whatever plans she makes now. So what should we do? So the resolution of the sophisticated agent is to compromise and choose consistent planning to optimize taking the future disobedience as a constraint. So that is when we optimize at the time t. Okay, so we assume that we have determined the future optimal controls, and then we just determine the A here. So let me put it in this way. So basically, the sophisticated agent is to imagine what herself will do in the future, and then assume that in the future she will take certain actions. Based on this information, optimize what we should do now. So this is basically the idea of so-called intrapersonal equilibrium. And we try to formulate the problem as a game, paying within the agents. And the agents are the herself in the future. So we are constructing such a game, and such a game will give us the equilibrium solution, and the equilibrium solution is associated with a consistent pen. So this is how we formulate this intrapersonal equilibrium. And this for illustration, and we are actually interested in the continuous time. So the extension of this idea to continuous time will be a bit non-trivial. So the free action of the agent has to be valid for a time period to make the control, because in continuous time, we cannot make controls at certain time point because that will not affect the problem overall. So we need to let the free action to be valid for a region, a very small region from T to T plus epsilon. And the T plus epsilon to capital T are actually fixed as this alpha equilibrium. So in this case, we can define what do we mean by intrapersonal equilibrium. And this intrapersonal equilibrium is the alpha EQ, such that for any X, any T, and the any A, we have this inequality. Okay, and this is how we define the intrapersonal equilibrium. And with this definition, Thomas Biot and his co-authors have already derived a very nice analytical framework for finding both equilibrium policy and also the equilibrium value function. So if we denote the V as the objective value of the equilibrium policy, and we have actually these two new notation U and G have a function set, and set is given as the expected value of X. And we also define the infinitesimal operator of the state process A as A. Then we can derive the extended XJB system that will drive the V, U, and the set. So I would like to remark that this V, U, and set have to be solved simultaneously. So they are coupled equations. So we have to solve them simultaneously. And the alpha is determined as the supremum realizing, is the control realizing the supremum. Okay. So here we have actually the verification theorem. So with some regularity assumptions, if V, U, and Z solve the extended XJB system above, then the alpha star is an intrapersonal equilibrium policy, and V is the corresponding equilibrium value function. And actually, this framework is nice, but there are actually quite a lot of open problems to be solved. And actually, this paper is trying to solve it. So here, I just extract the the last chapter of Thomas Biot's paper. So here I focus on one line here. A related open problem is to prove the existence and the uniqueness for the solutions of the extended XJB system. So now I will focus on a very specific case when G equals to 0. When G is not equals to 0, we need more advanced mathematical tools. So here, actually, in this paper, we still haven't considered G is non-zero, or G is non-linear function. So we just consider G equals to 0. And in this case, we know that the Vsy is equal to this U. And the extended XJB system is reduced to this nonlinear PDE. And here the alpha star realize the supremum of the Hamiltonian term. And we can see that this equation has been quite close to the non-local PDE we introduced at the beginning, right? And if we have the assumption about the reachability of the supremum, that is, we can actually find a map for the argmass of this Hamiltonian term per psi, then the alpha star can be represented as per psi of these arguments. And here you can see why we have these two terms. When we put in back this alpha star into this equation 3, then you can see the equation 3 will involve these two terms. So equation 3 is a special case of the non-local PDE we introduced at the very beginning. And we can even consider the stochastic differential utility. So I think this is a bit more advanced, and I mean it's a bit more tedious, and I would like to just give you the related equation. So here in this case, we consider utility is kind of recursive. So the YT will depend on Y itself, and the Y is basically the cost functional. And the Y is given by this BSDE. And we can also derive a sort of XJB equation. And in this paper, they call it equilibrium XJB equation. So that means if we want to solve for the value function or the optimal control, we just need to solve for this equilibrium XJB equation. And by the similar assumptions, we can also find that such a PDE that we need to solve is a special case of the non-local PDE we introduced earlier. But of course, here in this case, we have one more argument, the theta. The theta is basically the argument related to the U, because now our U will be like recursive utility. So that's why in finding our optimal control, we need to also have an argument about the U. So I think here I would like to summarize the research gaps we have. So even though we can, we have already obtained such an XJB, but the existency and the uniqueness of the solutions to this equation is actually still unknown to us. And actually, in this paper, they have solved the well-posedness problems for some special case. So they point out that the appearance of this term, the second order non-local derivatives, will bring some essential difficulties in establishing the well-posedness of the equilibrium XJB. So what they did is to assume that the diffusion coefficient of the control state process is independent of the control. So that may be good for some applications, but for most applications, for example, risk management, then we do want to have control in the diffusion term. So if we actually assume this, then the alpha star will be free of the this term, will be free of this UYY term. And in this case, actually the non-local PDE is actually a non-local quasi-linear parabolic PDE. So this is the research gap, because if we want to let the control enter the diffusion term, diffusion coefficient, so we need to study the non-local fully nonlinear parabolic PDE. And another research gap that is also not solved in this paper is that the G, we assume it to be zero or linear. So otherwise, we need more mathematical tools, maybe something related to the McKean-Fasov SDE. So I think it's not the focus of this paper, so I am going to skip this part. So actually what I have just did is to introduce you some background problems that lead to this very special PDE. So we call it non-local, fully nonlinear parabolic PDE. And the aim of this paper is to show the existence and uniqueness of this PDE. If we can do so, we solve the open problem left in the Thomas Biot's paper, or even Wei and Yong's paper. So now let's recall that the PDE we are interested in is this form. I think some notations also need to be changed. This should be S and S less than or equals to T. But I think mathematically speaking, it wouldn't affect too much. I'm sorry that I still mess up with the notation here. So we need to introduce the norms that people usually employ to study the fully nonlinear PDE. So they are actually a series of norms, and actually we are using this, the last one. Okay, So I think this is quite standard if you specialize in the PDE theory. And we also need to make some assumptions on the F. So F is the, this F, the nonlinear functional of the nonlinear functional generator of the right-hand side. And we need to have these three assumptions. So the first one is the ellipticity condition, and the second one is the Heuder continuity. The third one is the Lipschitz continuity. So for the second and the third one, we actually use a capital F. So capital F are the derivatives of the small f. So here the F are those with the text here. So actually we need to make a lot of assumptions on the second and even third derivatives of the F. But I think the good thing is that assumptions 2 and 3 are satisfied if F is the Frey's continuously differentiable with respect to all these arguments. So we need these assumptions, and actually these assumptions are also quite standard in the PDE theory, especially for the fully nonlinear PDE theory. So I would like to first give you the main results of this paper. That is under the assumptions 1, 2, 3, and given that the G is in a certain Banach space, the nonlocal fully nonlinear parabolic PDE admits a unique solution in this Banach space. So the space will be given later on because it's a bit technical. So here I would like to first make some observations about these results. The PDE is a fully nonlinear PDE, but not in a classic form, right? So we have already mentioned this. And regarding the proof of such a theorem, the well-posed theorem, so we actually realized that standard linearization does not work in this case. I think the main tricky part is about these three new terms, because they are not simply the differential operators. So we also have another steps to give the values to the t and x. So I think this is a bit special in terms of the formulation. And the third one we have also tried to explore is the using the weak solution or viscosity solutions to establish some well-posedness and then use some regularity arguments to reduce it to the classical solution. But I think actually, to the best of our knowledge, we think that it will encounter some fundamental issues, such as how the nonlocal derivative terms are defined. So that is in the framework of weak solution of the viscosity solutions, we actually have a very broad definitions on the derivatives. And now we even need to given the values after taking derivatives. So these two terms will be quite strange in the framework of the weak solution and the viscosity solution. So I think this is a very interesting future research direction. And here is the key ingredients of the proof. So now we are doing with such special PDE, and the overall idea is that we need to fix the nonlocal terms as some well-characterized echo functions. So that means we find some functions that are known, and then we replace the nonlocal terms by these function values. Then the PDE is reduced to a fully nonlinear PDE. So there is no longer the nonlocal terms. So we can then leverage the classical PDE theory. So of course, the functions that we pre-specify as echo functions will be very important, because that function should give us some nice properties such that we can replace it back. So that is the overall idea of the proof. So that is how we deal with the nonlocal terms. So our proof consists of the following key steps. So I list it as a key 1, key 2, key 3, and for the key 1, actually I think for each step, the results could be could be of its own interest. So the key one actually give an innovative linearization and the preservation procedures. So we first study a class of non-local linear parabolic PDE. And here we will do some sensitivity analysis, and then we will use the fixed point argument with the construction of the balance space and the contraction mapping over a short time horizon. And the second key step is to prove the so-called diagonal consistency of the solutions to the non-local PDE at diagonal. So here, I think I will give you the definitions later on. For the key three, it's like standard procedures to complete the proof. So the key one and the key two will be the most interesting part. And from the key one, actually, I think the results can be separate. So I would like to state the results here separately. So if we consider the following non-local nonlinear PDE here. So here, this non-local nonlinear PDE is quite special. Here we have add the LU. L is linear parabolic differential operator. Actually, it could be any linear parabolic differential operator with all real coefficients belonging to some space. And here we need to subtract the PU. The PU is given here. So it is a quite special operator. So the operator here, the PU is actually like a Taylor expansion up to the second order of the F with respect to the G, with respect to the initial value condition. So I think the special part of this P operator is the second line. So we not only just consider the second order derivative, but also given the values, T equals to S, X equal to Y. So this is very special. And the L cannot be P. So I mean the L as a linear parabolic differential operator cannot be P, because if L is equal, could be P, then actually we have done the whole proof for the general results. But we first focus on these special results. And we can prove that such a special class of the non-local nonlinear PDE meets a unique solution. So let's see how we do this. So in order to prove such a result, so it will be always good to first do the sensitivity analysis. So we actually, the technique we use is the Barnard's fixed points theorem. And to this end, we need to identify shadable function space and the contraction over it. So both construction of the function space and also the proof of the contraction needs us to analyze the sensitivity of the solutions of the parametric linear parabolic PDEs with respect to the parameters. And here the parameters you can keep in mind as the T and X, because earlier for our non-local PDE, T and S are like the external parameters. So basically the parameter we are referring to T and X. So we actually consider such a Cauchy problem. And L is a linear parabolic differential PDE with the parameter gamma. And all the terms, of course, will also be dependent on the gamma as well. And here is the result we have. So we can obtain the sensitivity equation of the solution U with respect to gamma. We denote it as U gamma. So this U gamma will satisfy this equation. I think the derivation of such an equation is very straightforward. Just differentiate the earlier PDE with respect to gamma. And more importantly, we can get the estimate of the norm of this U gamma. So this is very important result. And then we find that it will be bounded by the, this F is the inhomogeneous term. Sorry, here is some abuse of the notation. So this is the inhomogeneous term with the alpha norm and the F gamma with the alpha norm. And together with some classical result, classical PDE theory has already told us that the U can also be estimated with this upper bound. So we can obtain the following results. The U and E's derivative with respect to the parameter will be bounded by these two. Okay, so these results will be quite useful for us to construct the balance space here. So to investigate the PDE PDE of our interest, we will first consider the short time period from 0 to delta. So originally it was from 0 to capital T, but we first consider from 0 to delta. And taking advantage of the corollary that we have just derived, so we will consider the following function space. So the space is constructed in this way. So it is very keen in the sense that here we have three terms. The first term is the about the function itself, and the second and the third term is about the derivative with respect to the parameters. So sorry, the external parameter t and x. So it's actually not difficult to show that this norm is really a norm. It's really a norm under which the gamma is a balance space. So we are going to construct the contraction over this space. And in order to employ the fixed point theorem, we'll consider a co-subset U0 delta. And here the co-subset is that we fix the initial condition, and then for the solutions we consider a circle around the G. So the R should be large enough, but we fix the R such that it is a co-subset of the gamma. And then we study this operator lambda of U equals to V, where V is the solution to this PDE. This is actually a linear PDE because the U will be given, right? So given the U, such a PDE is a linear PDE. It's actually a classical linear PDE with external parameters T and X. So we shall show that for every U tilde and U hat in this co-subset, we can have this contraction. So if we have this contraction, basically what we have is that we can find the unique fixed point. If we can identify the unique fixed point, then you can imagine that we place the V by U, then you can see that the unique fixed point will be the solution we are trying to find. And we actually can prove the uniqueness, existency and uniqueness at once. So now this is very important for us to prove this contraction. And how we do, so actually we just take a difference, and then the difference will satisfy this PDE, this linear PDE, right? And this is the inhomogeneous terms we have. And then by the classical theory and also the sensitivity analysis before, so this one will be less than or equals to this, right? And then here actually we need very tedious derivations to really estimate these three terms. And in our paper, we have done these estimates, and we found that all these three terms will be bounded by this. I think it is very important here is that to notice that the work is interesting because the P is special. P is not a classical operator. And in these estimates, it's very important for us to split the delta term here, because delta term is something we can control. So we can set the delta such that the coefficient here is less than 1, such that we can consider the contraction, right? And with all these results, we can conclude that we have the contractions we have. So delta could be very small, could be as small as we want. So I later will show you how to extend it to the full horizon. So consequently, lambda is a contraction mapping from U to into itself, and by the fixed point theorem, there is a unique fixed point U bar, such that the lambda U bar equals to U bar. So the key one results follows. Okay, so we have first proved the key one results. And for the key 2, we try to actually key 1 results. We think the results can be separated out. And now for the key 2 and key 3, we somehow return back to the problem of our interest. So now we leverage the key 1 result and consider this operator. And this operator will be also well designed in the sense that we actually, you see, this is a linear parabolic operator, but here all the things are almost the same as the P, but here we do not give the values, so perhaps try to compare the L here and the P earlier we have been given. So we do not have this part. We do not have this part in the L. So this is the L, so this is the L we consider, and then we denote the U bar as the unique solution to this special non-local PDE. Then we notice that so the LU and PU have something in common. So when we consider T equals to S, X equals to Y for both of them, of course, then they will be equal. No, for all the U. So that's why if we taking the T equals to S and X equal to Y in the equation 5, we know that the U bar will also solve this PDE. So this PDE, you will not see the T and X anymore, and they are replaced by S and Y. So that's why you can see these 3 terms will be the same as these 3 terms. And this is the equation, we call it as non-local PDE at diagonal. So we consider this case by taking the T equals to S, X equal to Y is a diagonal case. So it's very interesting in the sense that for the equation 5, if we consider the diagonal case, it will give us the equation 6. But if we consider the general PDE equation 1 at diagonal, it will also be the equation 6. So this is the common part that we find between the key 1 result and the main results. So we need this results. So this result will be quite important. So this is what we call diagonal consistency. So this non-local PDE at diagonal equation 6, to the best of our knowledge, it should not admit a unique solution. But we say that actually we prove that if the V solve this solution, then the V at the diagonal will equals to the U bar here, because U bar also solve this non-local PDE at diagonal. So that would mean that even though we cannot prove the uniqueness of the non-local PDE at diagonal, but we found that they have some sort of consistency at diagonal for the solutions. So the here I think I only have time to give you the sketch of the proof. So the proof actually make use of the concept of the quotient space, and basically we consider the equivalent cars by defining the M, the capital M here is actually the function where they are here is actually the increment around the diagonal will be 0. So that means within the same class U plus M, so they will have the same diagonal consistency. So that means they have these equations. Then after we consider this equivalent class, we consider this quotient space. So this quotient space has the elements of the U plus M. And then we can consider some mappings. So some mappings from U to U, lambda U, and the lambda U UM, so that is given by this one. So if we consider these mappings, so we can first prove that U bar plus M is the unique fixed point of this operator, thanks to the fact that U bar is the unique fixed point of the lambda U. So here we have proved this before because U bar is the fixed point of the lambda. And then we can also show that V plus M is also a fixed point of this operator. So that is we just need to prove this fact by showing that the gamma V is diagonal consistent with V in the sense of 7. So we basically need to study the linear PD that drive these differences in a small neighborhood around the diagonal case, because we only need to care about the diagonal case. So we just need to limit ourselves to a small neighborhood around this diagonal case. So basically, based on these two facts, we know that V is also a fixed point, but here we have proved that U bar plus M is the unique fixed point. So that's why we must have V plus M equals to U bar plus M. And then that would mean that V and U bar will have the same, actually is in the same set. In the same set means that they have the diagonal consistency here. So the key two is very important, because I think the key three will resolve all the capacity and also give you the links between key one and key two. So key two implies that the solution to equation 1, the general non-local PD, if exists, must coincide with the U bar at diagonal, because the if we reduce the equation 1 at diagonal, that will give us the equation 6, right? So that's why if we have the solution, then it must also have the same diagonal consistency with the U bar. So in order to find the solution to the equation 1, we can consider this PDE. So this is the overall ideas that I mentioned earlier. We are going to replace the non-local term by the U bar, and then we consider this PDE. This PDE is actually a classical fully nonlinear PDE because U bar are long now. And for simplicity, we actually define the F bar as this F with the U bar. So that's why this auxiliary PDE becomes this one. And we can show that, okay, we can use the standard linearization procedure, add a L bar minus the L bar to consider such a contraction. We can prove that it is really a contraction, and that's why we can find a fixed point for this operator. So we can take a look at this mapping. So if there is a unique fixed point, then that will be, V will be replaced by U, right? V will be replaced by U, and then this term, the red terms, will be cancelled out. That's why we have the unique fixed point. We denote it as U star will solve this PDE. And this PDE will be very interesting because actually this is the unique solution to this PDE. The U star will be unique solution to this PDE. And we know that the U star also solves the non-local PDE at diagonal. So that's why the diagonal terms about the U bar in F bar can be replaced back by those of U star. So up to here, we have already proved that the U star solves the general non-local PDE equation 1. So this proves the existence of the non-local fully nonlinear parabolic PDE. And now we can actually claim that the solution to the equation 1 must be unique. Because if there is an alternative solution, alternative to the U star, then we know that this solution must also be diagonally consistent with the U bar, which will also be a fixed point of the theta. But theta has only one unique fixed point U star. So U star must be equals to this alternative solution. So this will lead to a contradiction. So the solution to the non-local PDE 1 must be unique. So based on these two, we have already established the existence and uniqueness of the general non-local PDE. And these results are established in a co-subset of the omega, right? So actually the extension to omega is actually quite standard. So I'm going to skip it. So we just need to assume that the point inside or outside, and then we can simply lead to the contradiction. So the extension is quite simple, quite standard. And now we have one more step to complete the proofs. We need to extend the results from a short time period to the full horizon. And here, until now, we just show the well-posedness of the solution in the short time horizon 0 to delta. So in order to extend it, so basically we can some sort of connecting the PDE problem. So we connecting the PDE problem from 0 to delta to 2 delta, and then 2 delta to 3 delta, and so on until we get the whole horizon, get the capital T. So we basically just revise our initial value condition as the U star T delta XY. So the U star is something we found from the problem with respect to 0 delta. Then we can actually complete the proof. We just need to repeat the procedures that we have for all the small intervals. Then we can basically get the full horizon. So basically that will complete the proof. So basically we have conclude the talk, and I think I have overrun a bit, but here will be some concluding remarks about my work, about this work. So I think the results here will be quite interesting and relevant, because we can prove that we can solve the open problem left in the Thomas Biot's paper. And we can, I think it's just partially, because for G as non-linear or not equals to 0, we still need to put some efforts into proving it. But I think another way we look at the problem is through the lens of the BSDE. So if we introduce the similar time inconsistent term in BSDE, that will become the BSVIE here. So if we add this term, so the parallel concept is the flow property of the SDE. So it will be finite for such a BSDE. And in this paper, they have proved that such a BSVIE will admit adaptive solutions of this form, and this U will solve the following, this non-local PDE. And here you can see that this non-local PDE is a quasi-linear PDE. So our work basically allows us to consider the second order BSVIE, which is on our research agenda. And I think this very last remark is also related to other theories in behavioral economics and finance. So especially for the prospect theory, whenever we consider the reference dependency, where we actually fix some point, that is what we refer to as the TX, right? If there is a reference related to some current time or initial times, then the problem solving will involve the non-local terms, and basically it will lead to the non-local PDE that we need to solve. So I think our theory will also be helpful in establishing the maybe continuous time prospect theory. And another one is about the regret theory. So I think it's quite recent advance in economics, and we can roughly conclude that for the regret theory, we will also have some sort of time inconsistency. So the problem can be formulated as the time inconsistent stochastic control problems that we introduced at the very beginning. So yeah, I think this is the concluding remarks for this work. Thank you very much for your attention. So please feel free to ask me any questions if we still have time.
Thank you, Patrick, for